For today's class, we'll be looking into basic algebraic identities, and that is under binomial expansion, still under polynomial. Suppose I have a plus b. So a is a monomial, b is another monomial. So a can be x, b can be y, a can be 2x, b can be 1, but we have two monomials. So if I raise this to the power of 0, we've already showed in indices that if anything is raised to the power of 0, the answer is 1. So if you now do a plus b, if you raise to the power of 1, anything raised to the power of 1 means that thing will be written again. For example, 2 to the power of 1 is still 2. So what if we now have a plus b all squared? So for this one, what will be the final answer? If I have a plus b all squared, some students will believe the answer is a squared plus b squared. This is wrong because a plus b all squared actually means we multiply a plus b by a plus b. By the time we expand, this a multiplies a plus b and the b multiplies a plus b, meaning this a multiplies this, then b multiplies this. So I'll be having a squared plus ab. B times a, alphabetically it is ab also, b times b squared. Then ab, they are like terms. 1ab plus 1ab, that makes what? 2ab plus b squared. So it is actually a squared plus 2ab plus b squared. We can go on and on. So if we have, let's say, a plus b or q, or with answer b, in that case we can say a plus b or q is a multiplied a plus b times a plus b times a plus b. Already we've established that a plus b times a plus b is this. So we can say for this one, let's take the first one as a plus b. Everything here becomes what we have here: a squared plus 2ab plus b squared. Let's expand and see what we are going to get here. So here we have a times a squared, that's a cube. A times 2ab, that's 2a squared b, because a times a is a squared. Then a times ab squared. A times b squared is ab squared. That is, we use this a to multiply everything. Now let's use b. So b times a squared, that's what? ba squared or ab squared. Alphabetically, b times 2ab. Initially we have 2a, then b times b squared. Then b times b squared will give us b cubed. So from here, we have some like terms. And where are they? We have a squared b. We have a squared b. So here a cube, 2a squared b, 1a squared b makes 3a squared b. Then we have 1ab squared, 2ab squared, that makes 3ab squared. Then with a b cube. So we can say finally that a plus b all cube equals to a cube plus 3a squared b plus 3ab squared plus b cube. And that is it. So these are basic algebraic identity for expansion, which you should know by heart, and this is the proof in case you are meant to expand. Now the question is, what if we have minus? So instead of having plus here, if you have to have a minus b, this remains 1. If I have minus here, this will be minus. If I have minus here, this becomes minus here. If I have minus here, then this is the trick now. This one is minus, this one will be plus, this one will be minus. We can actually try it. If you have to have a minus b, let me try to separate it so that you get it. So here it means if I have, let me start from this one. So it means if I have a minus b all squared, the answer is a squared minus 2ab plus b squared. You can show this yourself using the same formula. So here, if I have a minus b all cube, and we expand, we'll be having a cube minus 3a squared b plus 3ab squared minus b cube. So the pattern is, this one is always positive. Plus, minus, plus, minus. Plus, minus, plus, minus. So that is how the pattern goes. The first one is already positive. This time will be changing for negative. So this is binomial expansion. We can go on and on from a plus b all raised to the power 4 to 5 to 6 to n, but that will be in our next class. We will link down to binomial theorem, but we are not going that now. Today we want to focus on algebraic identities. So let me remove all these minus here since we have them there already. So you must know square of sum, square of difference, cube of sum, cube of difference. I used to sing about that song for my my students so that they can memorize it, because I do teach students in GSS 1, that is first level in junior high school. So that you must know square of sum, square of difference, cube of sum, cube of difference. That's the first part. Then we go to the factorization part. So, but the thing is, you have to know this by heart, so that anytime you want to expand square or cube, you don't need to be expanding. We just use the identity straight. Let's now move to factorization. For example, if we have square of sum, square of difference, cube of sum, cube of difference, what about sum of two squares? What about difference of two squares? What about sum of two cubes? What about difference of two cubes? For this, what will the identity? How are we going to go about this? Now let's take one by one. When you check this from this place, here we have a squared, we have b squared. If we can remove these two ab, we will let it only a squared and b squared. So we can say from a plus b all squared, which equals to a squared plus 2ab plus b squared. Let's make this two stand alone and let's bring one to the other side. So it means I'll be having a plus b all squared. This plus cross will become minus 2ab. Then I still have a squared plus b squared. So simply from here we can say a squared plus b squared equals to, what's the answer here? A plus b all squared minus 2ab. Done. But we can also do the same thing for this, because say we have a squared, we have plus b squared. So this is the second one. In the second one there, we have a minus b all squared from here equals to a squared minus 2ab plus b squared. We want to retain these two, so this minus 2ab bring it to this side. So we have a minus b all squared. When this minus crosses, it becomes plus 2ab equals to a squared plus b squared. So again, we've got another a squared plus b squared. So which means this a squared plus b squared can also be written as what? A minus b all squared plus 2ab. So this and this, they are the same and they have different uses. So we've answered this question. For this case, this is identity, or we use that other one. Now please note this down so that you can do that yourself. Write it down, please, the proof. Now let's move to the next one. You see this? This particular one is the most important identity in mathematics. And among all this, it looks simple, but it is most difficult to prove. It is most difficult to prove. So here, we call it difference of two squares. Difference of two squares. How can we prove this? Now suppose we have, let's say this is square of side A. So the area of this square, the area of this square is a squared. If you have a smaller square of side B, the area of this one is what? B squared. So our aim is to get the difference between a squared and b squared. Difference of two squares. How can we do this? So this second square here, let's put it inside here. So if from here to here is A, we know this part alone is B, so this is B. If from here to here is A, and this alone is B, the remaining part is going to be A minus B. Same way, from here to here is B, for what you have here. So if from here to here is B. Now if from here to here is A, it means from here to here is also A. If this one is B, the remaining part from here to here is also A minus B. So if you remove this square from this one, remove this small square from this square, this will be left. And that's our aim, to look for the area of this bigger square. And what will be the area of this one? Okay, we can try to do something like this. Let's join this one. That will be the area of this side plus the area of this side. So what's the area of this side alone? So this one times this become a rectangle. Length times breadth. That is A multiply A minus B. The area of this small one here is, if from H is B, this is also B. So that's B multiplying everything we have here. That is, we are adding B multiplying what? A minus B. So at the end of the day, A minus B is common. If we factorize A minus B, we left what? A plus B. So meaning the difference of these two squares, meaning A squared minus B squared equals to A minus B, A plus B. One of the most important identity in the whole of mathematics. So from here we can say simply, anytime we have something squared minus something squared, difference of two squared, we write A minus B, A plus B. I will emphasize, very important. So please note this before I wipe it off. And it can only be written just in a way, just one form, unlike this that has two forms. The remaining two, let's go on. Now for this particular one, A cube plus B cube. If you notice, we have A cube here, we have B cube here. So we can manipulate this, leaving A cube and B cube. Then these two take the other side. So from here it's obvious that A cube plus, A plus B all cube from cube of sum. So this is A cube plus 3A square B plus 3AB squared plus B cube. So in this case we can say A plus B all cube. Our aim is to retain A cube and B cube. So this plus 3A square B, bring it side, becomes minus 3A square B. This also crosses and comes minus 3AB squared equals to A cube plus B cube. From here it means A cube plus B cube equals to, now we want to write this left hand side, A plus B all cube minus 3A square B minus 3AB squared. Our aim is to get A cube plus B cube. Now from here we can write this as A plus B cube. Now when we check, minus is here, minus is here, we can factorize minus. 3 is here, 3 is here, we can factorize 3. A square A is common, B and B square B is common. So if we factorize minus 3AB, here we will let it only A, plus here we will let it only B. So we can either leave it this way, or we can go further. A cube plus B cube equals to, now we check these two. A plus B is common. A plus B all cube means A plus B 3 times. So that's A plus B all squared times A plus B. So if I write A plus B from both sides, this one will be left with what? A plus B all squared. Because out of this cube we've taken 1 away, minus 3AB. We've taken this AB out. So our A cube plus B cube becomes A plus B. Then here, if you expand this, we have A squared plus 2AB plus B squared. The expansion of A plus B all squared. Then minus 3AB. Then this becomes A cube plus B cube equals to A plus B. Then we have A squared. 2AB minus 3AB, that is minus AB plus B squared. So it has two forms. We either leave it this way. This is particularly important, especially when we are doing the question under sum and product of roots. And this one is the general one used. So either this or this. I'll write this one first, then this. Please always write this down in your notes, please. You will need it later. You make reference to it later. So the answer of this is ready. So it means A cube plus B cube equals to, writing this one, A plus B multiplied by A squared minus AB plus B squared. Or using this one, A cube plus B cube equals to A plus B all cube minus 3AB into A plus B. This is the one we use most times, but this one is particularly for root, sum and product of root of quadratic equation, which we are going to solve question on it. Okay, note this so that we can go to the next one. Okay, A cube minus B cube. A cube plus B cube, not useful. This is useful. Yeah, we have A cube, we have minus B cube. So we have to apply this one. So let's steal from this. We are having A minus B all cube to be equals to A cube minus 3A squared B plus 3 AB squared minus B cubed. So once we retain A cubed minus B cubed, this other will go to this side. So I'll be having A minus B all cubed. This minus cross can become plus 3A squared B. This plus cross can become minus 3AB squared. A cube remains, B cube remains. So let's write from the right hand side. It means A cube minus B cube equals to A minus B all cube plus 3A squared B minus 3AB squared. From here, A cube minus B cube becomes A minus B all cube. Then, notice 3 is common. A squared A, small a is the else HCF. B and B squared, B is the HCF. What we left here, A, this minus remains. What's left here, B. So we either stop it here, or we go further by saying A cube minus B cube equals to A minus B is common. If you bring out A minus B, what we left here will be A minus B all squared plus 3A. So this becomes A minus B into, if you expand A minus B all squared, A minus B all squared is its square of difference. That will be A squared minus 2AB plus B squared plus 3AB. From here, we'll be having A minus B into A squared minus 2AB plus 3AB, that is plus 1AB. Then plus B squared. So that is the second one. So this A cube minus B cube. So let's answer this question. For this one, what's the answer? The answer for the second one, A cube minus B cube equals to A minus B, A squared plus AB plus B squared from here. Or, using this one, A cube minus B cube equals to A minus B all cube, A minus B all cube plus 3AB into A minus B. Okay, note everything before I clean the board. Now let's summarize everything in here in a form we can easily remember. But before that, there's one more thing. Yeah, one more thing. That is, these two formulas, especially when we get to sum and product of what? Quadratic roots. To apply this, to get the difference A minus B in terms of what? A, B and A plus B may be difficult. So we have to combine this together. So from here, we are given that A squared plus B squared equals to A plus B all squared minus 2AB. And from the second one, A squared plus B squared is A minus B all squared plus 2AB. So since they are both A squared plus B squared, it means these two are the same. So if I have to equate both, it means A minus B all squared plus 2AB, this one here, equals to what we have up there. A plus B all squared minus 2AB. So our aim is to get A minus B. So let's take it to the other side. So A minus B all squared equals to A plus B all squared minus 2AB minus 2AB. From here, A minus B all squared equals A plus B all squared minus 2AB is minus 4AB. We take the root of both sides, it means A minus B equals to square root of A plus B all squared minus 4AB. Now, why is it so important? Why is it so important? I think we'll start with question whereby we are going to apply this. So let's go back to quadratic equation. Remember, for quadratic equation, without solving, we can always get the sum and the product of the roots. So the concept of alpha beta. Let's go to that. So note all this identity. I'll make reference to this later. So let's start with sum and product of roots of quadratic equation. Then after that, we use difference of two squared to solve questions. Then we'll now use other formulas too. So recall, for every quadratic equation of the form ax squared plus bx plus c equals to 0, it can also be expressed as s squared plus b over ax plus c over a equals 0 if we divide through by what? By a. Then, recall, if the root of this equation, after solving this equation, we are going to get to values of x. The first value is called alpha, and the second is called beta. Alpha and beta. So in this case, what happens? When we impute from these two roots, we can get the quadratic equation back. We've done it, can make reference to that. So we are going to get s squared minus alpha plus beta x plus alpha beta equals to 0. So meaning if I have any quadratic equation, it can be expressed this way. So without solving, you can always get the sum and the product of the root of the quadratic expression. For example, let's suppose you have a question like this. Find the sum and product of root of the quadratic equation 2x squared plus 3x minus 1 equals 0. So what are you going to do? We divide 2 by 2. So that it look like this form. So if we divide 2 by 2, we have s squared plus 3 over 2x minus 1 over 2 equals 0. What next? Write this identity below it. So s squared minus alpha plus beta x plus alpha beta equals 0. By comparing s squared, go with s squared. This x. So it means minus alpha plus beta equals 2 plus 3 over 2. All the things turn along. So by the time multiply both sides by minus 1, so we are going to get alpha plus beta to equals to minus 3 over 2. Just multiply both sides by minus 1. So this is sum of the roots. And the product here plus alpha beta equals to minus 1 over 2. So it means the product of the roots alpha beta equals to minus 1 over 2. So meaning without solving any quadratic equation, we can always get the value of what? Sum of the root and the product of the roots. Then you cannot be given a lot of questions whereby we always need to use what? To express the answer in terms of what? The sum and the product of the root. Let's take a typical example. With this, I believe if you are given any quadratic equation, you can always get the sum and the product easily. Divide through by the equation of s squared. If s squared doesn't have any coefficient, just compare straight. If it has, divide through. Sorry, it will always have a coefficient. So I mean, if it has 1 as coefficient, in this case, so don't to divide again, you just compare. Now, let's take a standard question whereby we are going to apply the identity we used the other time. But before that, let's do some recall. If I have alpha squared plus beta squared, that's similar to a squared plus b squared. If you go to the identity, the answer is what? A plus b all squared minus 2ab, or a minus b all squared plus 2ab, but this one is more useful. Then the second one is, what is alpha minus beta? The last one we proved. That is the square root of a plus b all squared minus 4 alpha beta. If you recall, the last one we proved. Then if you have difference of two squares, if you have alpha squared plus beta squared, the answer is what? Alpha minus beta, alpha plus beta. If you notice, you can always get alpha squared plus beta squared in terms of the sum of the root, product of the root, sum product. But for this one, alpha minus beta, we don't have the difference between the roots. That's why this formula is important. Before you can look for the difference of two square, you must know alpha minus beta, and that's when this one is useful. This for square. For cube also, alpha cube minus beta cube equals to alpha minus, let's use plus first, that's alpha plus beta all cube minus 3 alpha beta into alpha plus beta. Then lastly, if you have alpha cube minus beta cube, it is alpha minus beta all cube plus 3 alpha beta, alpha minus beta. All this identity, we've proven all of them already in the previous slide. So you must know all these by heart. So with this, you can solve any question of this form. So it is very important. All these are gotten from the identities. Now let's take a standard further math y question on this. So question of this form, they actually ask in further mathematics. Most times in normal mathematics for y they don't ask. But for further math and let's say German mathematics, you might be asked. So let's take a standard further math question on this. All right, we have an example already. Given that alpha and beta are the roots of the equation 2x squared minus 10x plus 8, find the following. So let's start step by step. With this question, I think this is enough example. Now, solution. The first thing to do, we have the equation 2x squared minus 10x plus 8 equals 0. The coefficient of s squared must be 1, like what we have here. So divide through by 2. So if we divide through by 2, we'll be having x squared minus 5x plus 4 equals 0. So let's write this below it. We have x squared minus alpha plus beta x plus alpha beta equals to 0. Then we are total for alpha plus beta. Alpha plus beta. We can get down directly. So note x, alpha plus beta is 5 minus. If the signs are the same, then the equation of x will be alpha plus beta. If not, it's going to be minus. Like what we have here. Because the signs are not the same. We are having minus here, plus here. So that's why I have a minus at the end of the day. But in this case, our answer is 5. We are done with the first part. Very quick. Second part, we are looking for alpha beta. That's the product. What's the product straight here? 4. As you can see, very simple. I told you math is very simple. Then the third one, we have 1 over beta plus 1 over alpha. Nah, we don't have it. We don't have beta and alpha alone. So what I meant to do, let's write this as a single fraction. The LCM is the product, that's alpha beta. Beta cancel beta, we have alpha times 1 alpha. Then we have plus here. Alpha cancel alpha, we have beta times 1 beta. So meaning, this actually what can be written in this form. What is alpha plus beta directly? It is 5 here. Alpha beta 4. As simple as that, as you can see. The third one, okay, this is the third one. The fourth one, we have to get what? Alpha squared minus beta squared. Alpha squared minus beta squared. Where is the identity? This is here. Is it minus or plus? Okay, it's plus first. For plus is it? That will be alpha plus beta all squared minus 2 alpha beta. So what is alpha plus beta? We've gotten it 5. 5 squared minus 2 alpha beta is 4. 5 squared 25. 2 times 4 8. Then by the time we subtract, we are going to get alpha squared plus beta squared to be what? 17. Then the next one, V. We are looking for what? Alpha minus beta. Where is the identity? This is it here. The square root of alpha plus beta all squared minus 4 alpha beta. And that becomes square root of alpha plus beta. Where is it? 5. 5 squared minus 4. Alpha beta is what? The product, 4. So this is what? The root of 25 minus 16. And that is the square root of 9. So it implies that alpha minus beta is plus or minus 3. We can just take the positive value, 3. Then VI, alpha squared minus beta squared. That's what? Difference of two squares. Where is it? So that's alpha minus beta, alpha plus beta. We already know alpha minus beta from here. That's 3. Then alpha plus beta, the sum, that is 5. 3 times 5, 15. So from here it means alpha squared minus beta squared equals to 15. VII, the seventh one, we have 3 over beta squared. 3 over beta squared minus 3 over alpha squared. Let's write as a single fraction. The LCM is their product, that is alpha squared plus beta squared, and that's alpha beta all squared. So from here, or let's just write it as, beside each other. Alpha squared, beta squared, alpha squared, beta squared. If beta squared cancels beta squared, you have alpha squared times 3, that will be 3 alpha squared. Minus alpha squared cancel alpha squared, we have beta squared times 3, that is minus 3 beta squared. So we check the numerator, 3 is common. That will be 3 into alpha squared minus beta squared over alpha beta all squared, because the square is common. Then that's 3. What is alpha squared minus beta squared? We've gotten it here already, 15. Over, then alpha beta all squared. What is alpha beta? The product, 4. 4 squared. So from here you can finish it yourself. Then the 8th one, we have alpha cube plus beta cube. Where is the identity? We have it here. So the identity is alpha plus beta all cube minus 3 alpha beta, alpha plus beta. Then let's impute the values. What is alpha plus beta? The sum of the roots, 5. That will be 5 cubed minus 3. What is alpha beta? Product, that is 4. What is alpha beta? 5. You can finish this yourself. The next one, ix. You have alpha cube minus beta cube. And what was it? Alpha cube minus beta cube. The identity is here. The last one here. That's alpha minus beta all cube plus 3 alpha beta, alpha minus beta. Now let's impute the values. Alpha minus beta has been gotten to be 3. That's 3 cube minus 3. Alpha beta, the product is going to be 4. Then alpha minus beta is 3. You can finish this yourself. Then for this last two, you can never find them here. You can't find them here. So you have to learn how to manipulate. You have to learn how to manipulate. So let's try to simplify this one, still using the idea of what? Difference of two squares. Like I said, difference of two squares is the most important. Anytime you see an identity that looks complex more than what you have here, remember difference of two squares. So note everything here. I want to clean it so that we can solve this. And I will add extra question. IXS. That's 12. I'll add one more. So let's clean the board and do the next one. Sorry, this one up to the beta cube, not beta squared. Okay, we have alpha x power 4 minus beta x power 4. How do you go about this? We know 4 is 2 times 2, so I can write as alpha squared all squared minus beta squared all squared. I didn't change anything because according to the law of indices, we can multiply this with power. Then from here, this alpha square is a single entity, so we now have difference of two squared. So what is inside if you apply this one? Anytime we have a squared minus another squared, we subtract, then we add. This time around we are going to add the whole of both alpha squared, beta squared, and subtract. So this becomes alpha squared minus beta squared. We subtract these two. Then we add alpha squared plus beta squared. As simple as that. And already from our calculation, we know the value of alpha squared minus beta squared. We've done that. We know alpha squared plus beta squared. We've done that. So just impute the value, and we are done. So the answer we got here, and the answer we got here, we have to add. We have to multiply, and that is it. xi, we have alpha raised to power 6 minus beta raised to power 6. Note, our aim is the difference of two squared. 2 have to be outside. So 6 is 3 times 2. So I can write as what? Alpha cube all squared minus beta cube all squared. Difference of two squares. So what happens? We subtract, then we add. By subtract, we have alpha cube minus beta cube. Then we add, we have alpha cube plus beta cube. Done. Already we have it here. Alpha cube minus beta cube, that will be the number 9. Alpha cube minus beta cube number 10. Sorry, number 8. So multiply the two answers, we get the answer, finish. Then xii, we can be told, find, here, okay, let's go, find, I want to write this question here. The quadratic equation, find the quadratic equation whose roots are alpha plus 1, beta plus 1. So these are the roots. But recall, for any quadratic equation, this is it here. The equation is x squared minus the sum of the root x, this sum, plus the product. I'm writing this one majorly to avoid confusion. So we are told that these are the roots. It means if you solve that equation, you get two answers. The first answer is alpha plus 1, beta plus 1. So to get the equation for this part, we have to get the sum. And what is the sum? The sum is we add. We are going to add alpha plus 1 and beta plus 1. So by adding, the sum becomes alpha plus beta, then 1 plus 1, that's 2. So the sum becomes, from here, the sum of the roots we got it to be 5. That's 5 plus 2. So it means the sum is 7. Then next we have to get the product. What's the product? We multiply the two roots. We multiply alpha plus 1 by beta plus 1. By the time we expand, we should be getting alpha beta plus beta plus 1. So that's the expansion for alpha plus 1, beta plus 1. Before now, we've gotten the product to be 4. And we've gotten the sum to be 5 plus 1. So the product is 10. So we are trying to find the quadratic equation whose roots are this. Since we already know alpha and beta in form of their sum and product. So we can now look for the equation. The equation is s squared minus, what's the sum? 7. That's 7x. Then plus, what is the product? 10. Equals to 0. So this is the quadratic equation we are looking for. So instead of giving alpha plus 1, beta plus 1, you can be told that whose roots are 2 alpha plus 1, 2 beta plus 1, or alpha square. No matter what you are given, you just know that we are adding the two to get the sum, multiply to get the product, then using this relation, you can finish it yourself. I believe with all this, you can solve any question pertaining to this. Then lastly, here we stop at power 4 and 6. If you have power 8 also, as far as the power is even, you can always express it this way. But the thing is, what if the power is odd? For example, you are told to look for the value of alpha raised to power 5 minus beta raised to power 5. In this case, you cannot use difference of the square directly because 5 cannot be expressed as what? 2 times anything. So if you have something like this, look for 2 numbers you can add to get 5. And 1 comes to my mind now, 4 and 1 or 3 and 2. So let's use 3 and 2. Using 3 and 2, go and do alpha cube plus beta cube, then alpha cube after alpha square minus beta square. We can expand this, or let's suppose what we have is plus first, so we use plus. So we expand this, alpha cube times alpha square is alpha raised to power 5. Then this one with this one will give us alpha cube beta squared, and this one will give us what? Alpha squared beta cube. The last one we are having beta raised to power 5. This is what you want to get. So meaning if we remove this, we can continue and say alpha raised to power 5 plus beta raised to power 5. This and this together. Then for these two, something is common. Alpha beta is common. So if I factorize alpha beta here, sorry, alpha square beta square is common. So we left with alpha plus beta. So if we remove this from this, we get this. So it means alpha raised to power 5 plus beta raised to power 5 equals to alpha cube plus beta cube, alpha squared plus beta squared, then minus this one. Remove from this. So we know alpha cube of beta cube already from here. Alpha square beta square from here. Then this alpha beta, this alpha plus beta. So no matter what you are given, you can always manipulate. The most important thing is to know that in mathematics, you can always manipulate. So I gave you this because if you go to advanced maths or if you go for some competition, these are the bases you need to know how to manipulate. So we are going to stop the class here for today. So tomorrow class, we will center our lecture on difference of two square alone. How to apply the identity a squared minus b squared equals to a minus b, a plus b. This looks simple. By the time you start some question involving this, you see that it is important we separate it alone as a topic. After learning that, then we'll now solve question on other identities generally. Then after that, we cannot go further on binomial expansion. You know, here we stop about 2 and 3. So we can have a plus b raised to power 5, raised to power 7, raised to power 20. If you have that case, what are we going to do? But before we move to that binomial expansion, there's a topic you have to learn first, which is what we call combinatories, permutation and combination, because we are going to use the idea of combination when we get to binomial theorem. So, but before that, we'll pause here. So in our next class, we'll move to different of two squares.